After watching this video lecture, students will be able to identify all the subatomic particles, including their mass, location, and charge. Students will be able to determine the number of protons, neutrons, and electrons in a particular isotope of an element. Students will be able to differentiate between atomic number and mass number of specific elements, and students will be able to define and understand what isotopes are. So the atom is the smallest particle of an element that has or retains the chemical properties of that element. And we've discussed this in the past, and we've discussed all the models of the atom, and we know that the atom is actually made up of a set of more simplistic particles. And these subatomic particles are known as protons, neutrons, electrons. And we're going to actually look at these protons, neutrons, and electrons, and we're going to be able to tell or identify where each of them belong in the atom, where we can find them, what the relative masses are of each of these particles, and the charges associated with each of these subatomic particles. So here we have a little chart. So first of all, we have our charge, and let's talk about charge first. Okay, so we have neutrons, protons, and electrons being represented here. I do want to point out, guys, you see these little symbols, letters with exponentials. N naught is going to represent neutrons. P with a +1 is going to represent protons, and E with a -1 is going to represent electrons. You'll see these written in lecture notes or in questions sometimes, and you can use them as shorthand, but just be familiar with that of the subatomic particle that each of them represent. Now, the superscript that is represented on each of these symbols you see here, or these abbreviations, correspond to the charge on the subatomic particle. So neutrons, they are neutral, they have no charge. Protons have a +1 charge, and electrons have a -1 charge. Now, the masses, or the relative masses, of each of the subatomic particles are listed here. Okay, as you notice, neutrons are slightly bigger than protons, and protons and neutrons are both much larger than the electron in terms of mass. Now, I don't expect you guys to memorize the numerical value or the mass number, or the atomic mass number. What I need you to do is to be familiar with their relative masses. So neutrons have a higher mass than protons, and protons have a much higher mass than electrons. So if we are familiar with their relative masses, you guys should be fine. Okay, now in terms of location, okay, the location of the neutron is in the nucleus, and we learned that last lecture. Okay, protons are also in the nucleus. Okay, they both reside in that small area inside the atom. Okay, and then the electrons, we know, orbit around the nucleus in their orbitals. Okay, so these are the charge, mass, and location identifiers of each of the 3 subatomic particles. Make sure you're familiar with each of them. Let's go ahead and let's refresh and reinforce some of the concepts that we've covered from our previous lecture. Okay, so the space occupied by electrons is way larger than the space that's occupied by the nucleus. A reference point for you would be something like a football stadium. So some of the larger football stadiums in the country hold somewhere around 100,000 people. So if we were to have that stadium and then take a golf ball and put it in the 50-yard line, that golf ball versus the size of the stadium would represent the ratio between the space the nucleus occupies, which would be represented by the golf ball, and then the remainder of the stadium would represent the space that the electrons occupy. Okay, so the space occupied by electrons is way larger. That was established from Rutherford's gold foil experiment. Okay, and what Rutherford established when he shot those alpha particles through the gold foil, and a lot of them passed through, was that most of the atom is empty space. Okay, and then if we go ahead and we look at the second thought here, the nucleus holds both protons and neutrons. Obviously, Rutherford discovered that the nucleus contained small positively charged particles. Okay, and so we're going to attribute that once again to him. And the neutron was discovered by Chadwick. Okay. The nucleus is more dense than the location of the electrons. Once again, that's going to be Rutherford. And and his gold foiled experiment. Okay, and once again, most of the volume of the atom is empty space. So Rutherford again. Okay, so we're familiar with all of these concepts that were explored and determined by Rutherford's experiments. We know that Chadwick discovered the neutron. Okay, and so we're pretty comfortable with all of these at this point. But there's a couple new concepts that we need to discuss in the context of the things that we are learning now. Okay, so we talked about the fact that there are both protons and electrons in the nucleus and that they have charges. Okay, so protons are going to be positively charged and electrons are negatively charged, and we just discussed this. Now, atoms are going to be uncharged. Okay, so atoms, the elements that we see on the periodic table are going to be uncharged. Why are they going to be uncharged? Because they have an equal number of protons and electrons. And so the charges, the positive and negative charges, offset one another. Okay? And then the sixth concept we're going to look at is that not all atoms have the same number of protons and neutrons. Okay, so although for a neutral atom, the electrons and protons will be equal, that's not going to be true for the neutrons and the protons. And we're going to discuss what this represents in a little bit here. So guys, we should have our periodic tables out for the next little bit. Okay, so we need to look at atomic number. So atomic number is represented by the letter Z, and that will come up a little later. But the atomic number is the number of protons that are in the nucleus. So if you look on your periodic table and you look above the carbon atom symbol on the periodic table, you will see a whole number 6. That 6 represents the number of protons in the element that it's above. So carbon will always have 6 protons. Okay, and when we're looking at that number, it is going to actually be used to help us identify that element. Okay, so the number of protons, or your atomic number, is always going to lead you to which element you're discussing or working with. Okay, so the atomic number, or the number of protons, identify the element. Okay, now some little bookkeeping things. We'll be seeing some subscripts next to element symbols. Okay, the subscripts on the left-hand side are going to represent the number of protons or the atomic number. And you'll see this come up a little bit later in the lecture, but just be familiar that the subscript here, when you just have the element symbol and the subscript written on the left-hand side, is representative of your atomic number. All right, so if we continue on now to mass number is represented by A. Okay, mass number is the number of protons plus the number of neutrons, so it's the summation. And it's always going to be a whole number because obviously you're adding physical subatomic particles. Okay, and it is not found on the periodic table. This is very important, guys. I need you to circle this and emphasize this. It is not found on the periodic table. This is a common mistake people make. I'm going to try to keep saying it, but please don't let the mistake be yours. Okay. In terms of the formatting that we were talking about on the previous slide, we talked about the subscripts written below representing the atomic number or the number of protons. The superscript in that same formatting represents the mass number, which is the sum of your protons and neutrons. So if we were to have the complete symbolism here, we would have a 6 written down here because the 6 would be the atomic number and this 12 is the mass number. So let's go ahead and look at some information about an element. Okay, so what is the mass number of an atom with 86 protons, 86 electrons, and 136 neutrons? Okay, now they want to know the mass number. Remember, the mass number is the sum of protons and neutrons. So if I look at my number of protons and neutrons, add them together, that's going to give me a mass number of 222. Okay, now that I've established the mass number, let's go ahead and identify the element. So what is the element? Now remember, the number of protons is always going to identify what element you are dealing with. So if we look at our atomic numbers off of the periodic table, go ahead and find that. Okay, and if you find that, you see 86 above Rn. Okay, Rn, or radon, is going to be the element that we're dealing with. And we've been able to identify how many protons and neutrons, or the mass number, the identity of the element, given just these simple pieces. I also want to point out, guys, notice you got 86 protons, 86 electrons. Remember that the elements on the periodic table are going to have balanced number of electrons and protons, and you subsequently get a neutral atom. Okay, so mass number, remember it's not on the periodic table. You have to, add up your protons and neutrons, but your atomic number will allow you to identify the element because it's always consistent, because protons stay constant. Hey, now some of you may have been wondering, why do we even care about the mass number? It's not on the periodic table. What's the importance? Okay, well, species called isotopes are actually really important to understand. Okay, so isotopes are atoms of the same element, but with a different mass due to the unique number of neutrons. Okay, so we already know that an element is defined or identified by the number of protons. Like, we're already familiar with that. Okay, so what changes is the fact that we don't have to have constant number of neutrons. Okay, there can be variable neutrons in the nucleus. Okay, and what happens there is that we know that neutrons are actually slightly heavier than protons. So what it does is it changes the mass of that particular version of the element. Okay, so an isotope, basically, hydrogen has a total of 3 isotopes. Hydrogen 1, 2, and 3. Okay, so this is just hydrogen, this is deuterium, and this is tritium. Okay, and they're almost all identical in properties, in terms of behaviors, and what we would see from our perspective. But in terms of like radioactivity and their masses, there's going to be differences in these atoms. Okay, so if we go ahead and we look at just our hydrogen. Okay, so your hydrogen here has a proton in the nucleus and a single electron on the outside. Okay, hydrogen, or deuterium here. Okay, deuterium has a proton and a neutron in the nucleus and that single electron. And then tritium has 2 neutrons and a proton in the nucleus, as well as that outermost electron. So you notice the protons are all the same in each of these isotopes, but the number of neutrons are variable. So these are all versions of hydrogen, but obviously they have slightly different characteristics. Now, how are we going to identify these, and how are we going to represent the fact that we're dealing with specific isotopes? We're going to use something called the hyphen notation. Okay, so your hyphen notation here, you're going to have the name of your element, a hyphen, and then the mass number. Okay, so this is beryllium 9. You're going to have beryllium hyphen 9 to represent that specific isotope. And given that we know the identity of the element, as well as the total number of protons and neutrons, we actually have information that will allow us to figure out how many neutrons are actually in the beryllium 9's nucleus. Okay, so if we take our 9 and subtract the number of protons, which is 4, quickly see that there are 5 neutrons inside this isotope's nucleus. Okay, and the same idea could be applied to any of these examples down here. Okay, so this is how we represent isotopes. Remember, isotopes are those elements, right? They're hydrogen, or they're oxygen, or they're nitrogen, but they have a variable number of neutrons.